Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel, please don't forget to subscribe, press the notification bell, and share my videos if you find them helpful to your studies. And I hope that while watching the videos that I made, you will learn a lot and you will enjoy watching. So let's have three examples on pressure on curved surfaces to highlight the principle. And aside from the principle, you have to recall your mathematics here, especially on geometry. So the tank in the figure is 3 meters wide into the screen or paper. Neglecting atmospheric pressure, compute the following using 9.79 kilonewtons per cubic meter as unit weight of water. Number 1, the vertical force on the quarter circle panel BC. Number 2, the magnitude of the resultant force on the quarter circle panel BC. And number 3, the angle that the resultant makes with the horizontal. So this is a basic problem for fluid pressure on curved surfaces. Take note that the tank is 3 meters wide perpendicular to the screen, so that to give you an idea, so we have here you have to locate the endpoints of the curve, then draw horizontal lines that defines the height of the projected area, which is this. So since it is 3 meters to the board, that means this dimension is 3 meters, and the height is of course 5 meters, the radius of this quarter panel. So in 3D, this is it. That's the dimension perpendicular to the screen or board. So for the vertical component of force, remember the principle that we have to draw vertical lines from the endpoints of that curve up to the liquid surface or imaginary liquid surface. Then the weight of the vertical component, which is defined as the weight of liquid above this curve. This is case 1. So the vertical component is downward, is equal to the volume of that real liquid or imaginary liquid bounded by the vertical lines through the end curves, the liquid surface or imaginary liquid surface, and the curve. So therefore, this is the volume to be considered in computing the vertical component of force. Now, since the width perpendicular to the board is 3 meters, the volume is simply area, this area here, times perpendicular to the board 3 meters. The area consists of area of this rectangle and the area of this quarter circle. Then you multiply that by 3 meters, that will become the volume. So to have an idea or imagination of the volume to be computed, so this is the other end, which looks the same as the front end, then that distance is 3 meters. So this is the centroid of the projected vertical area, which is a rectangle. Then the H bar or barred H or HCG is distance from free liquid surface, which is in this case water of specific weight 9.79, to the centroid of the projected area. So it is equal to 4 plus, because this is 5, 1 half of 5 is 2.5, so 4 plus 2.5 is 6.5. So for number 1, the vertical component, of course, it acts through the centroid of the volume, the vertical component, while the horizontal component is below, slightly below the centroid, because it acts through the center of pressure of the projected area. So that is FH. And for the vertical component, if this is the centroid or center of this length, then it also acts through the centroid. So remember, and FD is equal to specific weight of water times volume. Volume is area of rectangle plus area of quarter circle, then times width perpendicular to the board, which is 3 meters. So this is 3 meters also. So FV can now be computed. It is equal to 1164 kilonewtons. Then for the magnitude of the resultant force on the quarter circle panel BC, so before we can solve that magnitude of the resultant, by the way, by principle, that resultant passes through the center of the circle through the centroid, which is not O because O is the center of this front quarter circle, so it acts there. So for FH, it is gamma barred H area. So gamma of water 9.79, barred H is 6.5, and the projected area is 3 times 5. So FH is equal to 954.5 kilonewtons. So from here, we can now compute the resultant. So if this is the center of this 3-meter length, then it passes through the center of the quarter circle of that center also. So that's the principle. So that is FR. So from the figures, of course, FR is simply square root of Pythagoras theorem, FH square. So this is also the angle of inclination. Square root of FH square, square root of 954.5 square plus 1164 square. So FR is equal to 1,505 kilonewtons. Then finally, tangent of theta is equal to FV over FH. So tangent of theta equals 1164 divided by 954.5. So theta equals 50.65 degrees. So I hope that you are able to follow the solution and the explanation. Okay, let's proceed to the second problem, problem 7. The tank shown is 2.5 meters wide into the paper. Calculate the net horizontal force on the end panel, which is 3/4 circles. The net vertical force on the end panel. The line of action of the net vertical force from the vertical side AB. So that's the distance of the line of action of the net vertical force from the vertical side AB. So again, by principle, this is the 3/4 panel BD. By principle, for the horizontal force, so we need to have the height of the vertical projection of area because the width perpendicular to the board is 2.5, so it's constant. So we draw lines from B and D, horizontal lines, then that defines the height of the vertical projected area. So since this is 1.8, the radius of this 3/4 circle panel, so that's also 1.8, and the width perpendicular to the board is 2.5 as stated in the problem. So that FH is acting leftward and it is below the centroid of this projected area. Since this total height is 4, then barred H is equal to 4 minus, of course, half of 1.8.9. So 4 minus 0.9 is 3.1. So barred H is 3.1. This is the location of FH. It is slightly below the centroid of the projected area, and the distance is this called E sub V from that centroid, and it is below. So for FH, it is specific weight of uh, oil with specific gravity 0.82, then barred H area. So gamma of oil is 0.82 times 9.81. Then the barred H is 3.1, then the area is 2.5 times 1.8. So FH is equal to 112.22 kilonewtons. Now for the net vertical force on the end panel, so by principle, after we locate the endpoints, we draw vertical lines to the imaginary or real oil surface, liquid surface. Then this is the oil surface, that's the boundary, and this is also the boundary, which is the curve. So the volume to be considered in computing the weight or vertical component of force is simply the volume enclosed by these vertical lines through the endpoints, this oil surface, and this curve here. And for us to easily compute that volume, we divide it into rectangular volume and this 3/4 quarter of a circle. So this is FV. So FV is equal to specific weight of oil times volume of oil. So specific weight of oil times this area, which consists of area of rectangle and 3/4 quarter of a circle, times width perpendicular to the board, which is 2.5. So FV is equal to 0.82 times 9.81. The area is 1.8 times 4 plus 3/4 of pi 1.8 square, then times quantity 2.5. So solving for FV, FV is equal to 298.32 kilonewtons. Then for the third, for the distance of the line of action of the net vertical force from the vertical side, that distance is, we can compute that into many ways. One is by Varignon's theorem, uh, the areas must be decomposed into area of rectangle, area of quarter circle, then area of this semicircle here, so that it's easy for us to compute this distance. Another one is you can decompose the area into rectangle and 3/4 quarter of a circle, or this sector here, wherein there is distance for the centroid of a sector, which is 2r sine theta over 3 theta, where theta is half of this angle, half of 270 degrees. So that's 135 degrees. Remember that. And the third one, which I present now, is the easiest among the possible solutions, which is we use the fact that because this is circular, the resultant of the components passes through the center of this 3/4 quarter of a circle. Because the resultant passes through that center of 3/4 quarter of a circle, if we sum up moment about that point, which we will call point O, then the moment of the resultant is 0 about that point. So by Varignon's theorem, the moment of the resultant, which is 0, is equal to the sum of the moments of its components. So one is counterclockwise, the other is clockwise. So one is positive, the other is negative, then equate to 0. From there, we can solve that distance. So we will call that center of this 3/4 quarter of a circle as O. So by Varignon's theorem, I'll present the third solution. Summation moment O equals 0 because the moment of the resultant about O is 0. But before that, let's solve for this vertical distance of FH from the centroid of the projected area as E sub V. E sub V is equal to height of rectangle square over 12 bar H. So this is the equation, summation moment about O, counterclockwise positive. So FH times this distance is zero point 0.9, half of 1.8, 0.9 minus E sub V, then minus FV times X sub AB equals FR times 0, or 0. So E sub V is again height of rectangle square, which is 1.8 square over 12 times bar H, and bar H is 3.1. So E sub V is 1.8 square over 12 times 3.1. So E sub V is equal to 0.0871 meter. So substitute into this equation because we already found FH and FV. So 112.22 times 0.9 minus 0.0871 minus 298.32 times XAB equals 0. So from there, we can now solve XAB. XAB is equal to 0.3058 meters. So that's it. So the third question just applies the principle that the resultant passes through the center of this circular curve. For our last problem for this topic, problem 8, a sphere of radius zero point 0.6 meter fits snugly into a circular opening at the bottom of the containing vessel with a diameter of 0.6 meter. The liquid in the container is oil with specific gravity of 0.8. Compute the volume where an upward force acts. Number 2, compute the net weight of oil that tends to push the sphere downward. Then number 3, determine the minimum weight of sphere so that it will not be dislodged. So this problem is different from the first two because in the first two, the width perpendicular to the board is constant and the volume is just area of the front times width perpendicular to the board. This time, remember, this is a sphere. And the endpoints of the curve, which is in contact with the liquid, is no longer a point, but rather there are so many points, infinite number of points, because this is circular. All the periphery of this circle or the circumference of the circle are in contact. That's the end of the curve, in contact with this liquid. So there's so many lines that must be drawn. So that is, we draw this line and there are so many lines. In fact, this is a cylinder, right? Circular cylinder. And considering this curve here, which is equal to this curve here, which is also there is curve in front and at the back, just concentrate on this curve first. This is both case 1 and case 2. So for the lower curve, this is case 2. For the upper curve, this is case 1. So FV is going down. For the lower curve, it is case 1, so the force is upward. And it is supposedly equal to the volume above this curve to the liquid surface. But because we have here case 1, which is downward, if we remove that, if we remove the volume above the curve, then the net volume would be this volume here, which is also equal to that. And actually, if you imagine, this volume is the volume when this area here, which is a segment of a circle, is revolved about this axis. So that you can imagine that volume. Before that, let's have this elements first. The height of this, because this is a spherical segment, this is also a spherical segment. The height, we denote that by h. This is also h. Then this is the top view so that you can imagine. So this is the sphere, this is the hole, and this shaded part between the hole and this sphere here is the volume to be considered. It's just like a volume where a buoyant force acts, and that volume is equal to the volume when we revolve this segment of a circle around or about this axis here, vertical axis. So I hope that you can imagine that. That volume, therefore, is equal to volume of sphere minus volume of this right circular cylinder, then minus 2 times volume of this spherical segment. So the remaining volume is the volume where an upward force acts. So actually this volume here. So again, it is that volume where an upward force acts is equal to the volume of sphere minus volume of this circular cylinder minus 2 times volume of this spherical segment. Because if we consider this part here, there are two cases. One is below, where we have to consider volume above this lower curve. Then we have this another case which is downward. The force is downward, so the net volume to be considered is this, and we revolve that about the vertical axis, because if you position yourself here, it is this volume here. If you in this current position, we are here, this position. That's why we can only see this. So if you revolve that around this vertical axis here, then it generates this volume here. And that volume, again, as I said, is equal to volume of sphere minus volume of this right circular cylinder minus twice the volume of this spherical segment. So this is V1, which is where FV1 acts and it is upward. So it's just like buoyant force. FV1 is like the buoyant force, net buoyant force. So V1 equals volume of sphere minus volume of circular cylinder minus twice volume of spherical segment. So this is the height of the cylinder, volume of cylinder, this one, the whole of this, then volume of spherical segment, another volume of spherical segment. So to solve for the height, we have to consider this right triangle here. This radius is radius of sphere, which is 0.6, and this is 0.3 because half of the whole diameter, so 0.3, that's the radius. Then this is half of the height of the cylinder, 8 sub c over 2. By Pythagoras theorem, 8 sub c over 2 quantity square equals 0.6 square minus 0.3 square. So 8 sub c over 2 is equal to 0.3 square root of 3 meter. So therefore, that's 8 sub c over 2. The height of the cylinder is 0.6 square root of 3. So height h therefore is radius of sphere 0.6 minus half the height of cylinder. So this is 0.6 minus half the height of the cylinder is this height h here. So 0.6 minus 0.3 square root of 3, in decimal that's 0.080385 meter. That's the height of the spherical segment. So volume 1 is equal to volume of sphere 4/3 pi 0.6 cube. Volume of cylinder is pi 0.3 square minus pi 0.3 square times height of cylinder 0.6 square root of 3. Then minus 2 times volume of spherical segment. The volume of spherical segment is with one base is pi h square over 3, quantity 3 times radius of sphere minus h. So minus 2 times pi, height of h, which is 0.080385 square over 3, 3 times radius of sphere minus h, which is 0.080385. So computing each volume of sphere is 0.90478 minus volume of cylinder, which is 0.29384 minus 2 times volume of one spherical segment is 0.01164. So that volume is equal to 0.5877 cubic meter. Then compute the net weight of oil that tends to push the sphere downward. So if we consider this part, we have here portion of the spherical segment and above it is oil. So because this is weight of oil, FV, weight of oil, so weight of oil is equal to volume of this cylinder surmounting this portion here, then less, because there is no oil here, this is volume of spherical segment minus volume of spherical segment. So volume, weight of oil, which is going down, is equal to gamma times weight of this cylinder here, cylinder 1, let's call that volume of cylinder 1. So weight of oil is equal to gamma of oil, volume of oil, and the volume of oil is volume of cylinder 1 minus volume of spherical segment, which is 0.01164. So volume of cylinder 1 is pi 0.3 square, the radius is 0.3, and the height is 0.6 plus h. So volume of cylinder 1 is pi times 0.3 square times 0.6 plus 0.080385 h. So that's the height of this cylinder here. Then volume C1 is equal to 0.19237 cubic meters. So substitute here to solve for the weight of oil. So 0.8 times 9,810, let's express the weight in newtons. VC1 is 0.19237 minus volume of spherical segment 0.01164. So volume or weight of oil is equal to 1418.4 newtons. Finally, to solve for the minimum weight of sphere so that it will not be dislodged from this position here. So we have here FV1, which is specific weight of oil times V1, then minus weight of oil minus weight minimum equals 0. Summation forces Y equals 0. So FV1 minus weight minus WO equals 0, or weight should be greater equal to, the minimum weight is greater equal to FV1 minus weight of oil from this equation here. So W equals greater than equal to 0.8 times 9,810 specific weight of oil times V1, which is 0.5877 minus weight of oil, which is 1418.4. So that minimum weight should be 3,193.87, or say the weight should be greater than equal to 3,194 newtons. So that's it for this video, and I hope that you will subscribe so that in my next videos you can also watch them, and hopefully you can uh, understand my presentation of the solution. So bye bye.